The bird, I think for the birds we're giving methods workshops throughout the years, and in the past few years, I have given workshops on the topics of analysis of longitudinal data. I gave two of them. One is focused on the so-called marginal models with generalized estimating equations, which are also often called GE. So that's GE approach. And the second workshop is focused on the random effects or mixed effects models. So this is the third one in the series where we plan to expand the scope into a so-called more intensive longitudinal data, or we sometimes also in statistical literature also call it functional data. And I mentioned earlier to Susan that this topic is like a relatively advanced topic, even for like statistics or advanced biostatistics major. So my goal today is to just give a brief overview in terms of what data we are looking at, what are the challenges for analyzing those type of data, and what are some of the popular tools. And I hope to avoid too much technical details and to give you some ideas. If you can walk away sort of getting a little bit better idea of the main concept and what analysis or what can you get from this type of data, that will be very helpful. But if you actually do need to analyze those type of data, I would recommend consider seeking help from a statistician. Yeah, so that with that, I'll get started. Uh, so first I'll start with acknowledgement. So like some of the materials from this are coming from a few textbooks. For example, this book called Semi-Parametric Regression. Oh, sorry. Semi-parametric regression is mainly talking about smoothing, non-parametric smoothing, or curve fitting techniques using a random mixed effects model framework. And the second book is called Functional Data Analysis. This is a classic textbook talking about, all sorts of issues and how do we analyze those type of data. And then the last one is called Functional Data Analysis, which is relatively recent book. It has a little bit more applied and implementation flavor. So it give you quite a few examples and give you very specific R codes. So people wanted to try this analysis can just using the codes and run on those data sets to get like more hands-on experience. And also I also borrowed some lecture notes from Dr. Josh Hooker from University of Pennsylvania. He's an expert in this area. I think his notes is mostly follow this book called Functional Data Analysis, this one in the middle. So I would assume that this audience, for the most people are non-statistical major, like maybe a scientist in epidemiology or public health in general, or you just maybe just wanted to interested in so this type of techniques. But I do assume that most of you have general knowledge about basic statistics tools like linear regression, logistic regression, Poisson regression, for example. And then there's maybe some familiarity with matrix algebra. So finally, since this intensive longitudinal data is, like extension of standard longitudinal data, so I assume some familiarity with basic concept and the main analysis tools with longitudinal data as well. So here's the outline of this workshop. I've started by introducing the type of data we are looking at, and then I'll spend some time on non-parametric smoothing or basically curve fitting, because for intensive longitudinal data, you have like very dense measurements even for within each subject, right? So we wanted to fit a curve very more flexibly. So that's kind of is for the curve fitting of smoothing. So that's the first part, and then afterwards we'll look at the intensive longitudinal data or functional data. We consider exploratory analysis. So how do we try to get a basic understanding of the mean trajectories, the variations in the data, and a very important exploratory tool, which is principal component analysis. And then the next part, I will talk about some like formal regression analysis. So what we call functional regression, or we could also consider clustering methods on those data. And then I'll end with some discussion. Okay, so first, so what is what are intensive longitudinal data or functional data? And I also have to say that these terms, they are the meanings are very similar, but they are probably not exactly the same in the sense that they may be used in different contexts. I think intensive longitudinal data, I see that term used maybe a little bit more often in like a psychosocial or this type of a context. And it really means, if you look at the name, of course, it's a longitudinal data. You have repeated measurements over time. But the intensive meaning that you have like a typical longitudinal data is you probably only have a few measurements, like maybe somewhere between 2 and up to maybe 6, 7, or even up to 10. But then if you have something more than that, you can typically call them intensive longitudinal data. And functional data is a term that's probably used more in for among statisticians. And this term, it means like basically your basic units of the data. It's not one number, it's not a vector, but it's like an entire curve. It could be an entire image or a general, which or called a general function. Right? So more rigorously speaking, functional data is like it's more general terminology. But I think for the sake of this talk, I would also look at functional data, which is also measured over time. So I'm trying to, I probably will use these two terms interchangeably in this workshop. Um, and so as Brian mentioned earlier, the context where we often get intensive measurements is oftentimes with, you have, especially using wearable or mobile devices, because with those devices, it's much easier or it's much less expensive to get, a large number of measurements, even for the same subject. So here are a few examples. Sorry. The first one is we can, for example, get daily measurements on our scientific target. For example, it could be you get weather data for each day, and you could have like mobile-based diary reports. So in this figure, what I show is Canadian weather data from the functional data analysis book. So this data says there are 35 different weather stations across Canada. For each weather station, for every day, they will record the temperature and also precipitation levels on each day. So so in so you can see for each of the curve represent one weather station, you have 365 measurements across 1 year, right? So the x-axis is day, y-axis is temperature levels. So every weather station have one curve like this. And then now we have 35 in total. So basically the data is like we have a sample of 35 different curves, right? They are obviously much more intensive than our typical longitudinal data. The second example is something called ecological momentary assessments, or EMA. I assume that maybe some of the audience may be familiar with the term. I know that in some studies, in one study, for example, I was involved in where we try to understand the relationship between food security and glycemic control among diabetic patients. So we actually did utilize the so-called EMA. So the essence is like use smartphone to push very frequent surveys to participants. So in our study, we push survey up to 4 or 5 different time per day, and we typically choose some try to make the time like more random, and then we collect data up to about 20 days. Now here, this is an example, where let's see the outcome is a mood, like generally how do you feel, and then So as you can see, there are multiple measurements per day and up to 20 days. Then you get this very dense, very intensive measurements, probably somewhere around 80 to 100 data points for each participant. This is again another example of intensive longitudinal data or functional data. The third example is from wearable devices or wearable sensors in some behavior interventions or behavior observational studies, such as physical activity. Myself, I was involved in many studies that use wearable accelerometers or heart rate monitors to try to understand people's physical activity patterns. Now those devices, they typically give us higher resolution, higher dimensional measurements. In this figure, I'm showing an example of accelerometer data for one participant for 2 days. So the data were downloaded in like so-called 1 minute level epochs, meaning you get one number for each minute, basically summarizing the activity level within that minute. So every day, we have up to 24 hours, so that's about 1,400 time points measurements per day, right? As in everybody, we also typically ask people to wear the device up to 7 days. So then you get everybody have about 10,000, observations. This again, intense longitudinal data or functional data. The next example is another project I was involved in, where we are interested in measuring adherence in HIV prevention trials. Where we use something called a wise pill. It is like it is a medication dispenser. Like the bottle. It has, I think it has cell phone chip on it. So if you open the bottle, we can receive a signal. So in essence, we will know for each person. We ask them, for example, to take pills for 2 times per day. And so from the signal, we are able to tell how many times they have opened the bottle. So on the left-hand side, showing the data we observed for each day. It can be 0, 1, or 2. White means they did not open the bottle at all. Like the light shade meaning they opened 1 times. The darker shade meaning they opened 2 times per day. So again, in this example, everybody have measurements for up to 1 year. So this is another example of you have this intensive measurements. On the right-hand side, we did a little bit of a processing or smoothing in the sense that let's say, using a 7-day window. Within 7 days, we try to calculate what is the adherence, the percentage of adherence, meaning like, let's see, if they are supposed to take the pill 14 times per week, so how many times they actually did open the bottle. So you can calculate the percentage. So this is showing, adherence levels for different participants. Some of them are highly adherent, so it's almost closer to 100%. Some people, are less adherent, right? Some of them, especially for this participant, is starting off at about 50%, but then levels off, and at some point it's like almost not adherent at all. So we see a lot of variations and patterns in this type of data. So the last example I'll illustrate is from another project with Dr. Jonathan Breaker at Hutch, so where we use smartphone apps for smoking cessation. And the app is, I think they put a lot of thoughts in designing a app that's hopefully help people, really motivate people in sort of continuing with smoking cessation, but then app is only useful if people use it, right? So they published some promising results, but we also wanted to look at the engagement levels. So here the measure we use are number of logins per week. So the study was conducted for about 1 year, so about 52 weeks, and then what I'm showing here is for each week, how many logins did we recorded. So this is like a few examples, like some people, they kind of, uh, they started, at the beginning, it's probably about 4 times per week, as in gradually, they gradually decrease. I guess it's not surprising, right? But then this person in green, he probably keep using the app until maybe around like 20 weeks, as in the usage is much more sparse after that. But then there are other subjects who really only use the data for the first few weeks, and then they stop using it. Right. So this is kind of another example. You have again very intense measurements over time for each individual. Yeah. So overall, so just this I just give you some examples. So overall, so we can see that we can view them as still as longitudinal data, but they are different from our typical sense of longitudinal data. Is the most obvious feature is like really dense versus sparse, right? Uh, and then because you have more dense, more intensive measurements. So we actually have more information to model the detailed, shapes of the trajectories and also variabilities, both within subject and between subject. But what I mean by within subject or between subject is like, especially let's consider the physical activity example, right? You have people's physical activity levels across multiple days, as in you can see how their movement patterns differ across days, right? You can also see how different people have different patterns. And in terms of a time scale, the intensive longitudinal data generally tend to be, we maybe more look at minutes, hours, or days, or weeks, as opposed to, months or years, typical longitudinal study. To sort of give a bit of a contrast, I mean, this example I used in previous workshops for a typical longitudinal data example. This case, we're looking at growth curves in terms of weight for 48 pigs. And you still each individual still have a trajectory, but the data are really only observed at about 5 different time points. So the curve is really connecting all those 5 dots, right? So because the data are sparse, then the shapes are relatively simpler, right? So in this case, probably a linear growth curve can already capture the shape pretty well. And also wanted to mention briefly, a few, I guess, to highlight the difference between a few different types of data. So if we use the notation of Yij and Xij to denote the outcomes and covariates or predictors, for I to index individuals, there are n individuals in total. J indicates the number of measurements per subject. So there are m of them in total. So when, in our typical setting where we have independent data, so everybody is independent, you only get one measurement per subject, right? So that's kind of like we use standard regression in that case. M is 1, and we typically have a larger number of individuals. So we're kind of try to draw conclusions from those data. And then the other extreme is the time series, where you probably only have one individual, and then but you have a lot of measurements for that particular individual, right? You can think about, let's see, like let's say stock market, for example, like SP 500. You check the values per day over a long time. But for this time series data, so you don't have independent units, right? So all the measurements are sort of correlated with each other, even though the correlation probably is stronger if the 2 time points are closer together. Yeah. So these are the two more like extremes. The longitudinal data or this intensive longitudinal data. Somewhere, both of them are kind of somewhere in between, right? So you have a bunch of individuals, but you also have repeated measurements. Where they differ, so they all generally assume that you have a larger number of subjects or samples, so that we can draw conclusions. But longitudinal data, you have like a small m. So again, sparse, and for intensive longitudinal data or functional data, it's much more dense. So big N here. Yeah, and so what are the implications of this in terms of analysis? So because longitudinal data are, I think everybody here probably already knows that in longitudinal analysis, the most important aspect is we try to account for the within subject correlations. And then there are two popular techniques for doing that. One is using a so-called GE type of methods, where you assume some sort of a working correlation structure, and then so you can estimate all the parameters, and making inferences. And the other approach is using random effects to account for the correlation. So it can be linear mixed effects models or generalized mixed effects models. But for both approaches, a common theme is that the shape of trajectories is typically relatively simple. What I mean by that is because the data are sparse, so typically we can maybe sort of assume a linear trajectories, right? Or sometimes you can also throw in a quadratic term to allow some sort of a non-linearity, but we probably only use like only a few parameters to describe the trajectory. These are relatively simple. And also the covariance correlation structure is also relatively simple in the sense that for GE, you are assuming that something like exchangeable correlation or autoregressive correlation using probably one parameter or two parameters. For random effects models, I think most of the time people just use random intercept and random slope. Again, I think these are sufficient for sparse data. This is a kind of a giving more specifically, for GE, we have built some model for the mean structure, and we assume a working correlation. The linear mixed effects models, you can use like a random intercept and random slope here. Um, um, but for now, if we switch gear to the intensive longitudinal data, now we still need to account for this within subject correlations. But because the data are much more intensive and much more dense, so the two implications are, so the shape of trajectories probably are much more complex. You would see all kinds of, different types of shapes and the curvatures. So usually a linear model would not be sufficient. We wanted to try nonlinear model. But also I also want to add that as I mentioned earlier, in longitudinal data, you can also add in a quadratic term to allow for nonlinear. But that's also still not very flexible in the sense that it's assumed certain types of nonlinearity, right? It may be appropriate in some cases, but generally speaking, it is still somewhat limited. So we wanted to sort of not assuming any type of shapes and letting data dictate what shape it should be. And in terms of the covariance or correlation structure, it can also be much more complicated. So because of that, like a GE approach or a simple random effects approach would not be sufficient. So that's why in this context, we generally try to use models that are much more flexible and making less assumptions. So those methods, what we typically call nonparametric methods. So yeah, I think that's for the introduction. So I think I'll maybe just pause very briefly and see if there are any questions so far. I think I just look at the chat. I don't see any questions.
Nothing in the chat yet, Chongzhi.
Okay, thank you, Brian. Yeah,
But we can pause for a minute if people have questions.
yeah. So, if anybody have questions, feel free to unmute yourself or type in the chat. Okay, so if not, then I'll continue to the next part, which is nonparametric smoothing, or you can think of that as a curve fitting. I mean, this is the part where the focus is looking at each one individual. Like, as I mentioned before, even for one individual, you have very dense measurements. So if we sort of, and, of course, you can just, connect all the dots and then, but then as we know, this data are typically very noisy, right? If connects the dots, they kind of are very wiggly and then they are contaminated by noise. So we want to generally, we think, a more smooth shape reflects the signal much better, so much more accurately. So the first part is trying to, for each individual and with all the measurement, let's try to fit a smooth curve. Um, and there are actually many different methods to do that in the statistical literature. I think for the audience, I know some of you probably have used some of those in your analysis as well. So, for example, there are something called kernel smoothing or local polynomial smoothing, something called, and also spline smoothing. Most of the techniques, I think they would work fine. So in this, as long as you choose your smoothing parameter carefully, they would all of you that those techniques can give you desirable results. In this workshop, I'll focus more on the spline smoothing because I think that integrates a little bit better with the other parts of the workshop, which is like principal component analysis and the regression parts. Um, so this is an example. I think the data is from that functional data analysis book. It's a MedFly. I think it's the egg counts from MedFlies. So this is showing data from one of the flies, and then so this, as you can see, so there are some data points start somewhere around here, and then these are all the data points. So we wanted to fit a flexible curve to reflect what we think is like the mean signals. And then, of course, in practice, they are all contaminated by noise. So if you actually connect the dots directly, it's too wiggly, right? Um, So this will get a little more technical now. So the approach I'm going to take for this workshop is so-called spline based methods. So the idea is we're trying to find a set of so-called basis functions. So we assume that the observed data yi is equal to signal plus noise. Signal is a underlying smooth function, which is x evaluated at a time time ti. But then there's also a noise, epsilon I on it. So what we actually observe is yi, but we wanted to use some methods to estimate this smooth process x. So we try to use a set of basis functions to represent. So you can think of basis as one example is like you can use polynomials, right? You can maybe you start with, let's see, I want to fit a linear regression. I just put like an intercept and I'll put a time t on it. It will be like a linear shape, right? But I know that's not flexible enough, so maybe let's add a square term. And if we want to be more flexible, we can keep adding like cubic term, right? So in this case, all those kind of the intercept will be 1 t squared, t cubic. This will become a basis. And then in general, you can choose like more other type of basis as well. But the point being, each basis represent a particular types of shapes, right? If you use a combination of basis functions, you would allow a very flexible family of possible shapes. And we talked about the polynomial basis as example, but if you actually use polynomials in practice, you probably would find that they are not very stable to use in the sense that, depending on the the numbers, right? If t is big, those numbers get big really quickly, and also you might have like strong correlations between, let's say, t and t square, right? So there's a lot of properties that's not very desirable for polynomials. So B-spline basis is another it's sort of like a modified version of polynomials. The idea is you kind of divide your time that you're considering. Like in this case, from 0 to 25, you divide them into many small intervals, right? And then you would construct some basis functions which are non-zero only in two of these intervals. And in this case, for example, one basis function is like it has zero values here, but then it's non-zero in this interval and becomes zero otherwise, right? Another basis could be maybe starts from here, zero, and become non-zero, jump up and goes down and becomes zero again, right? So this left-hand side is not very smooth. The right-hand side is a little bit more smoother. So they are determined by the order of polynomials. But I guess the point I want you to take is like, so basically, you try to divide your time into different intervals, and you try to design your basis functions to capture some local features in a small region. You have this one, you have another one, you have another one. And each one of them is probably not flexible enough, but if you use a combination of them, they can capture a very flexible type of shapes. So if we use this type of splines um, to try to do a curve fitting, this is what we would get. If you use this kind of more like change point type of splines, you would end up fitting a curve, something like this, right? It fits the data, I think, pretty well. But of course, people might ask, are there really a change point over here, right? Is this like really sharp changes over here? So we wanted to get more smooth fitting. So we can use more smooth basis functions. The right-hand side is what we are getting. So this is seems pretty reasonable. And this is kind of giving you still the same this curve fitting, but showing you the shape of basis and why it can capture, all this kind of a curvature. So all the dashed lines here are really the shapes of each individual basis function. So you can see this peak, for example, is probably captured by this basis, and this probably captured by this. Again, I think the point is really like, you have many of those basis functions. Each one captures some aspects of the nonlinearity. By using a combination of them, you are able to sort of accommodate a very flexible types of trajectories. Okay, so once we choose the set of bases, so what do we do next? So how do we actually get the curve fitting? One obvious answer is how about let's use least squares, like as linear regression, like you choose a set of basis functions, and then you put them in the model like as if it's a linear function. Let's say you put something like, you put it 1t squared in the model, you can do or least square fitting, right? This approach sounds good, but there's some challenge with is the performance depending on how the choice of basis functions. So basically, there are two choices. Number one, what are the types of basis functions you will choose, right? Do you choose those piecewise linear functions allowing change points, or do you choose more smooth ones? And also, how many basis functions do we need, right? So statistics is all about the trade-offs or compromises. So if we choose the number of basis functions, if we choose it too small, what usually happens is your model is probably not flexible enough. Thinking about, let's say you just use a linear, only a single linear function, you choose 1 and t as your basis, right? It's not going to be flexible enough. But then if you choose too many of them, it's also not the best in the sense that you are probably going to overfit. So the most extreme case, let's say if you have like maybe 25 data points, if you choose 25 bases, then what you end up doing is actually connects all the dots. So it become too wiggly and overfit data. So the fitted curves is too rough. So what we hope to do to like achieve somewhat of a compromise in the middle. So not too smooth, not too rough. Uh, so that is what we call so-called penalized spline smoothing approach. So the idea of this is that, we try to start with relatively large number bases because we want to be accommodate a very flexible type of shape. Because if you are started with a small number, you are limited. So we want to start with a large number bases. But then to avoid the overfitting problem, we try to add some called smoothness constraints, or sometimes we also call the regularization. So in the sense is that we try to minimize, try to find the smooth curve X, and then we try to minimize the prediction error. But in the same, we don't want to get very weakly fitting. So we sorry. Um, so we would add a penalty term. The penalty term, roughly speaking, would mean is the roughness of your curve. So thinking about the more wiggly it is, the larger the penalty is. And the lambda is a parameter, what we typically call smoothing parameter. It controls the balance between between your model fitting and your roughness or smoothness. So in the sense that if you, let's say, have the lambda close to 0, means you are not doing any penalty at all, right? So you're actually encouraging that very weakly fitting. You just try, you probably will fit the data really well. You might even fit the data perfectly, but it probably will be very rough, not smooth at all. On the other end, if you let lambda to be really big or even approach infinity, so it'll give a more way to smoothness. You are guaranteed to get a very smooth fit. But the problem is that you might not fit the data too well. So we typically want to choose a lambda somewhere in between. So this is a little bit too abstract, but like if you look at this figure, hopefully illustrates the idea a little bit better. So the left-hand side is a case where your smoothing parameter is too big, meaning you are really concerned. I want to guarantee a very smooth fit. In this case, it's very smooth, right? But the problem is does not fit the data very well. Have larger residuals here and also here. A second case is like the smoothing parameter is very small. So like you are just mainly concerned about model fitting. So you fit the data, observe the data really well, but it's just not smooth enough, right? And then so you probably overfit the data. So the right hand side, so we choose a lambda is somewhere in between. And as you can see, it's probably achieve a reasonable balance in that it's still a smooth function, but on the other hand, it is still fit so the trend of the trajectories reasonably well. Um, and I'm sorry, I think that's a little bit, uh, yeah, it didn't, for some reason, it did not show up in the right format here. So overall, sort of if you want to use penalized spline smoothing, so the procedure is we typically choose a sufficiently large number of basis functions. I would say at least 10. I typically use somewhere maybe 20 or even up to 50, depending on, the type of the data you're looking at. And then we use the so-called roughness penalty. And the penalty, we typically choose derivatives of the curves because, if derivatives is large, meaning it changes very quickly, right? So if we wanted to control the derivative, so it's kind of the change is more smooth. And there's also like a concept called effective degree of freedom. I'll mention very briefly. it is essentially saying that roughly speaking, so how many terms do you use? Sort of equivalent, how many sort of terms do you use in your regression? So if you fit a linear model, you have two terms, degree freedom is 2. If you use k basis functions, just do a least square, the degree freedom is like maybe k, like 20 or something. In this case, since it's kind of like somewhere in the middle, right? So effective degree freedom is probably more like somewhere around 5 or 6. So this is something you don't need to know how they are calculated, but I think it will be helpful to understand that, for any kind of smoothing, there is always some tuning parameter that controls how smooth that is. It's to really try to balance how well you fit the data versus how smooth your curve is. And that parameter will also, roughly speaking, tell you the number of degree freedom. And in terms of how to choosing smoothing parameters, there are existing methods developed by statisticians. So if you need to use that, generally we use cross-validation types of approach, again, to sort of try to get a balance between model fitting and smoothness. So this figure try to illustrate how how the methods work in terms of choosing smoother parameters. I think you have seen these three figures above. This is like a too smooth, probably lambda too big. This is too rough. Lambda is probably too small. And this here is a case where the lambda is about just right. So on the right-hand side, I'm showing you some of the x-axis, showing you different lambda values, the smoothing parameter values. On the y-axis, it shows us cross-validated error rate. So what I wanted to point out is, like, in this case, if it is too smooth, it's most likely it's somewhere. Oh, sorry, it's somewhere around here. So like the lambda is really big. If it's too rough, it's likely somewhere on the left side. Its lambda is really small. As you can see, on both the left and right side, so the prediction error typically goes down and then goes up again. So yeah, if you choose the lambda just right, typically you can sort of achieve a good balance. You will minimize the cross-validated error. So yeah, so that's how it works in practice. Yeah. Um, okay. And I think so. My goal of walking through this is to sort of give you an idea of how this method works. You don't need to know sort of the technical details of all the formula or how do you calculate that. In practice, if you actually need to use penalized splines in your project, so there are well-developed R packages. For example, there's package I use the most is called MGCV. It's very easy to use, and I think I will show you an example of how that works. I didn't put this in the slides because from a quick Google search, there are I can find many very nice resources available. Some are tutorials or slides. So they develop some are like have interactive courses. So they will show you step by step. They give you example data. They show you the R codes to implement this, and they show you the results. They are integrated very nicely. I give you a few links or a few ones I think are really good. So yeah, so I think that will wrap up this part. So I will maybe show you very quickly how that works in practice. But are there any questions at this point?
Nothing in the chat, Chongzhi.
Okay, thank you, Brian. So I will. Um, stop sharing the slides and then go to one of the tutorials to give to walk you through briefly how that works. Okay.
Susan has a question, Chongzhi.
Susan, yeah, please.
Okay, gotta get to the right pointer. Unmute. I just one quick one was, in a given field, to what extent has there been some sort of like convergence on like what is the right shape to use for like smoking cessation, or are there places where you're sort of saying, okay, well, this is what most people are using, therefore I'm going to probably not, sort of rely on the data as much. Yeah, does that sort of come out like with the fitness data? Is it really like, are there certain sort of areas of research that have just sort of said this is the best shape to use?
Yeah, that's a great question. So the approach I just walked through is really more like a data, using the data to decide what is the right balance, right? So like in that case, for example, the figure I showed is really try to use cross-validated error. You try to minimize that, see what do we get. But I do want to see that it's really important to understand that the any procedure sometimes work well, sometimes not work so well, right? So I think this type of automatic procedure, in my experience, it generally work out pretty well. But there are, if in your particular application, I do think, your scientific knowledge, your expertise, your hypothesis, they are really useful too. In the sense that, if yeah, if you sort of know that you expect certain types of a smoothie or certain types of trajectories, you might I think you can use this to your advantage in the sense that you can choose more appropriate basis functions. In the sense, I know in some contexts, like you have seen this kind of a lot of local peaks and valleys. So in that case, it's your typical polynomial or like even B-spline may not be the best choice, like something like a wavelet might be a better choice. In some cases, like signal processing, like maybe Fourier basis, better choices, right? So this is for this has for the basis function selection, and also for the smoother parameter as well. I think it's important to not just trust the output from the software. You also wanted to make sure that you plot the data and see if it sounds reasonable or not. If it doesn't seem reasonable, I would consider manually change those parameters, make them a little bit bigger, a little bit smaller, and then see which kind of maybe seems more appropriate in your setting. Yeah, I think the context, it is indeed very important. Okay, so let's this is like I think it's like a short course. So it's one of those links. So I'll just walk you through some examples. So this I think they're showing the data they're showing is like you have basically you try to fit a curve, you have X and Y. Obviously looking at the data, they are, a straight line doesn't work well, maybe even quadratic doesn't work well, right? There's curvatures in a few different places. So, and then it will show you if you were to fit a linear model, right? If you use the R codes here, you simply use the LM function, fit a linear relationships, then this is your model fitting, right? The orange line is fitted regression line. It also gives you the shaded areas are 95% confidence regions of the mean. So obviously it doesn't fit the trajectory very well from a visual check. And then, so if we wanted to use the penalized splines, actually, it's really easy to send the code, right? You just load the R package called mgcv, and then the function is called GAM. GAM means generalized additive models. So just use this GAM function instead of LM. So you're going to have the specified outcome, which is Y, and then on the right-hand side, previously we just said x, right? So that means a linear relationship with x. Here we just say s of x, meaning I wanted to allow the covariate x to have a nonlinear relationship, right? It's very easy to use, and then when you do that, you actually can get this fitting. So the model, this function, internal function with MGCV package, they have a bunch of default options. So if you don't know too much technical detail, you don't need to change much of the default options. Just use the default options. Most likely it's a B-splines as your basis. Most likely using something like GCV as your smoothing parameter selection, and they give you a model fitting like this, right? The purple line is a fitted curve, and it also gives you a 95% confidence bands of the curves. So I assume that everybody agrees that this fits the data much better than the linear fitting, right? Let's see. This is kind of a trying to show how it works, like for why, for example, why it could capture all these curvatures there. So the colored line is really showing you the basis functions they are using internally. So you can see there's like, let's see, there's a local peak here. So this is probably captured by this line here, right? And then yeah, so you can actually pinpoint exactly, and it's to give you sort of a visual idea of why this sort of basis expansion approach can capture the various shapes in the trajectories. And then it will give you some outputs. So I don't think I'll go to the details of this. Let's see if we can okay, so this part I just wanted to mention briefly, like as I mentioned earlier, and also related to Susan's question, this package typically will give you automatically choose a smoothing parameter for you, but sometimes, after visualizing the data, you might not be happy with that choice, right? You think, well, fading is probably a little bit too weakly to my likes, or it's a little bit too smooth. So you might want to play with the smoothing parameter a little bit. I think they do allow you to do that within the GAN function. You can specify something like SP. SP stands for smoothing parameter. You can choose that value to maybe some like 0.1 or 0.01. You can try different choices and see how it looks. Let me see if we can get it. I'm not sure if I can get it running right now, but hopefully you got the idea. So okay, I think that's all I wanted to see in terms of implementation here. Okay, so I think in the previous part we mainly talk about how to fit individual curves. And for the next part, I think next hour, I hope to talk a little bit about how do we explore, understand this type of data, and how do we what type of analysis we can do for this type of data. Still, again, this is like this is really kind of more like advanced topics in statistics. So probably like more like so I try to maybe mostly focus on the concepts and the main ideas, and there will be some notations or formulas, but yeah, you don't have to worry too much if you can walk away knowing, what data are they and what type of analysis we can get from that. I think that will be that'll be good. So for um I I will start with exploratory analysis of functional data. So just with any, if we think about what are the first thing we learn in statistics, right? We start learning, what if we get some data, as in how do we understand the distribution of the data, like the mean, what is average values, what is the variations, the variance, the standard deviations, right? So for this functional data or intensive longitudinal data, similar thing. So we first wanted to understand what are the most important features. Let's see the mean and variance, covariance, right? So the mean part is really easy and intuitive, right? I'm again using this MATLAB data where you see we have probably somewhere around 30 to 40 different curves, trajectories, right? If I wanted to understand what is the average shape or trajectories, it's relatively easy, right? You can take for at each time point, we can take the average, and then you can connect the dots together. If they are too weakly, you could do some sort of smoothing as well. But you can estimate this kind of average trajectory pretty well. And they are really easy to understand, right? They are really seeing that at each time point, what is the sort of the average values of the accounts, right? And then you can from the average shape, you can also get some intuition of less for the average trajectories is kind of a slowly increasing at the beginning, as in probably reach a peak somewhere around maybe let's see 7 or 8 days, and then it gradually decline afterwards, right? So it's easy to calculate, easy to interpret. Now let's try the variance or covariance. Now, unfortunately, this is where it starts to become really complicated, right? If you think, if we think about if we have like a one random variable, and then we calculate the variance, it's just one number, right? It tells us the variability in the data, right? If the number is big, it means it's spread out really wide. If it's really small, it's kind of the variability is kind of very close to the mean, right? So that's very easy. And if you think about like multivariate data, you have a few different variables, right? We will start to look at variance covariance matrix. We wouldn't wanted to look at the variance for each variable. And then we also look at the covariance or correlation between two different variables, right? So in that case, we have a matrix. That's when the number of variables is not too big. So that's still okay, right? We can look at the matrix and know, which variables have larger variations, and which variables has smaller variations, and which two variables tend to, correlate more highly with each other. That sort of thing. But when you are looking at this intensive or functional data, then the problem is that you have very dense measurements, right? And if you think about the variance covariance matrix, it's like very big. Let's see if you have 100 measurements per subject, right? So you're going to have 100 by 100 covariance matrix. And conceptually, we can even think of them more like continuously for any time s and any time of t. You can define this covariance, and then you can estimate this by sample covariances, right? You of course it's not difficult to calculate. Once we calculate that, it is like it's like an image now, right? In this three-dimensional place, it's an image. So we get this covariance matrix, but what does this really mean, right? So it's really hard to even understand what this means. So and of course, you can pinpoint at, if you choose one S or one T, you can probably say, well, that's the amount of correlation or covariance they have, but still you feel like you don't get a good big picture, in terms of what variations are there in the data. So because of those challenges, and also, because the data are really dense, there are just simply many, many possible directions of variations. What I mean by that, the two curves can differ from each other in many, many different ways, right? Because of that, it's hard we have to rely on some additional techniques even for this exploratory analysis. So the technique that is used very often in this context is called principal component analysis, or we typically term it functional principal component analysis. Now this is if some of you are familiar with what principal component analysis does in multivariate context, this may be a little bit easier for you because really the concept is similar, except that you just have many different variables. They are kind of ordered along the direction of time, right? But if not, I hope still hope to, there are quite a few different concepts. I hope to maybe illustrate using some toy examples. So hopefully you get the idea. So in this example, I sort of simulated 20 different curves. So each of them, they are indicated using different colors. So, first, before I showing you what a PCA would do, you might want to observe and think. So what are the type of variations you see among these curves, meaning how these different curves are different from each other? So maybe one of the most obvious one is it seems like there are this kind of up and down shift of this whole curve, the curves as a whole, right? If you, for example, look at this purple curve, it tends to have higher values throughout different times, right? So it's tend to stay at the top, as whereas this curve is kind of always lower at any time. So this kind of like more like this kind of seems to be one very obvious features. But then of course you may also notice other type of variations in the sense that many curves like have a peak or valley somewhere around here, right? So we observe a few different ones, and then if you want to make a guess, what is like the most obvious one or most dominant one? You probably would guess it's probably the up and down shift, right? So that's actually exactly what the first principle component is capturing. So in this case, the first principal component actually the so-called eigenfunction or eigenvector is you think of that as a direction of variations. In this case, it's a constant function. What that means is that for each of the curve, right? Let's see this purple curve here. I would um, try to represent that as like a multiple of these constant functions. For example, I would probably choose, let's see, I take the average of these values, right? And I make like a flat function from here. So that would be a good approximation of this purple curve right there. For this, like a little, I don't know how we call it, like a pinkish, purplish, sort of a curve. Again, if I just, I can make a constant function, let's say using the average value, make a constant function. I mean, I do not get it back to exactly the curve, but it's very close, right? So for each curve, as long as, I can find a flat curve of that to approximate the original ones reasonably well. So that's what we call the first principal component. So basically, you try to find one direction because there are potentially many, many directions. So we look for all type of directions to see which direction can capture most of the variation, meaning which direction you can use to approximate the original curves the best. So the best one you found is called the first principal component. In this case, we found that it can explain about 85% of the total variations. That's already really like the majority of variations there, right? And then, so if you are still not happy with that, you want to see, oh, what additional features can I extract? So what we can do is we'll take the difference between the original curve and this first principal component, right? If you take the difference, calculate the residuals, you'll get the curve in this figure. So what you observe, you look at the variation. So like the variation is really big across all time points in the original data, right? But once you take out the first principal component, so you can see, the first principal component contains a lot of variations, and the residuals only have like much smaller variations left, right? So in reality, this 85%, this is about 15%. But at this point, if you want to see, I want to see what are additional types of variations in this figure, right? So you probably will notice they generally have this kind of like sine types or cosine type of shapes, right? Some of them start high and become low and become high again. Some of them are in the opposite direction, start low, increases, and then decreases, right? So in fact, if we are doing the second, try to find the second principal component, that's the exact direction we are getting as well. So the direction is indicated by this type of curve. It goes down and up. And again, we can approximate each of these curves by a scaled version of this shape, right? Some of them, like let's see, this blue curve is probably more like, I would say maybe something like a 0.6 times this direction. You have this basically similar shape, but the magnitude is just a little bit smaller. Some of them, this green curve is going the opposite direction. What that means is like it's probably loaded negatively on this direction, right? The PC score so would be some of them will be positive, some of them will be negative, but direction is really the same. The direction by direction, I mean how different curves vary from each other. It's always have this type of pattern. And we found out this component explains about 14% of the total variation. So if we remove this from this figure, so you can see the variation left is even smaller, right? So actually, this is about only 1% of the total variation from the original data. Now, of course, if you wanted to continue, you can find the third principal component, which has this kind of a sine type of a shape. And we can estimate that it actually explains the last 1% of the total variation. So hopefully this example give you some idea that like what the PCA does. It does two things. Number one is it helps us to find out what are the sort of most important or most obvious directions of variation, because in reality there are many of them, but they are not created equal, right? Some of them are more important, some are less important. So we hope to find the most important ones, and we also quantify their importance by the amount of variation they explains. In this case, like 85%, 14%, or 1%, right? And by doing that way, so you kind of have some control of, if you wanted to explain, let's say 90% variation, you can, if you only choose two directions, that's sufficiently large. So this is the second purpose of this is like really about dimension reduction. Like again, the original data is really high dimensional, it's really intensive. So you can extract many features. But if you are doing PCA, we can maybe only keep the first two features only, but you already know that you keep most of the information in the data, even with only two features, right? So, yeah.
Chongzhi, there's a question in the chat. What does each line represent? Are those individual trajectories?
Oh, yes, yeah, yes, thanks. Yeah, that's right. Each line is the individual trajectories. That's exactly right. Yeah.
Thank you.
Okay, so yeah, so that's hopefully through this example you can get a rough idea of how PCA works. Now from this PCA, so we generally get three information out. Number one is the directions, right? Direction is really basically the shape of the variations you have. In this component one is really the constant function. That's the direction we are looking at. The principal component two, the direction is this kind of shape. PC3 is this kind of shape. So these dashed lines, these are called directions, or we also call them eigenfunctions. And then the second component you get is really how much variation are explained in that direction, right? In this case, it's 85% for component one, 14% for component two, 1% for component three. So they tell us how important are each of the directions. As because these are ordered decreasingly, so it also we can also use this information to decide how many components we wanted to keep, right? So in the sense that, most people oftentimes maybe choose a threshold. Let's see, if you wanted to explain about 90% of variation or 95% of variation, then you will decide maybe I will only keep the first two. That's sufficiently large. Yeah. And then there's a third component. It's called the principal component score. So those, I think you can think of them as more like as uh, a summary or a summary score of the or one feature from the original trajectories, right? So an example would be if we know that the first principal component, the direction is really like this kind of flat curve, right? The principal component score in this case would actually be the average values. For each curve, you maybe have 100 observations, but you can calculate the average value. It's just one number, right? If you use just one number and create a flat line as that value, that's kind of already a good approximation of the original curve, right? But that one number, that average value, is your principal component score. So you can think of you extract one feature, but we know that that feature is really, really important. Yeah. So I think I'll go back to the methods part a little bit. I think so hopefully this now would be a little bit easier to understand. So how we do this is, in practice is we first try to find a direction that explains the most variations, and that direction is what we often call the first eigenfunction or eigenvector. And then we can also estimate the amount of variation that's explained in that direction. That's our eigenvalue. Um, and then, so that's the first one. But after you find the first one, you wanted to, take out the variation explained in this direction and find, and then find the next direction that explains the most variation is the remaining ones, right? You just keep going and until you find all these directions. And as I mentioned earlier, so the eigenvalues are in non-increasing order, meaning the first one is always the most important, explains the most variation. The second one explains a smaller amount of variation. So you have this very nice ordering. And then the type of directions or eigenfunctions, they are orthogonal to each other, meaning that the different features you get, they will be uncorrelated with each other. That's like a very nice property to have. The PC score, I think, is you really can think of them as like a summary score of the ice curve or individual trajectory on the jet direction. So so from the original data, it's like xi of t, it's like a very dense trajectory. But from the PCA, you reduce them to like a finite number of PC scores, like a DI1 up to DIJ, and each of them is a feature, right? So typically, we only need the J to be relatively small. So that's how we achieve dimension reduction, right? So originally you may have 100 observations. You may find like maybe 3 or 4 of those PC scores. They are sufficiently enough to keep most of the information in the data. We have seen this example before, and in terms of how we actually do it, I think so. There's one issue I didn't mention. I mentioned briefly, but like how do we choose number of components? So so what typically we can create a plot like this called a script plot. What this shows is like on the x-axis is the PC component, like PC the first component, the second, so on and so forth. And then the y-axis is how much variance were explained by each component, right? In the previous example, it would be like 85%, 14%, 1%. So when we analyze the MATLAB data, so the first one explains about 60% of the variation. The second one, close to 30%. Next one is probably somewhere around 7% also. and then it goes down really quickly, right? The fourth one, maybe 3 or 4%. Once you go to the fifth one, it's probably, somewhere around only 1% or 2%. For a lot of data sets, they typically have this type of shape. It actually goes down pretty rapidly. So that's a good thing, because that meaning that we can probably take the first two or maybe three components that can sort of give us most of the information. And then we from if we do a PCA, we are able to get the average the mean function. We're able to estimate, like in this case, if we keep four different directions, we estimate the so-called eigenfunctions of the first four components. And then this figure shows a shape, right? But looking at the shape itself, it's still not very intuitive. So what do those really mean? So we typically create a visualization, something like this, to hopefully make it a little bit more intuitive to understand the types of variations. So the way these things work is that each of the this is showing principal component 1, 2, 3, and 4. Let's use the first one as example. So we try to plot three different curves. The one in the middle is the mean curve, mean trajectories. It's really like the average curve over here. Then we create two additional curves. By adding, you can, have the mean subtract the direction you are talking about. And also you have the mean plus the direction you are talking about. So for principal component number one, so really would be, this is like a mean minus PC1. This is like the mean trajectory. This is the mean plus PC1. So what this tells you is really, I'm giving you three typical examples of trajectories, right? They are only different in their first principal component. So you can get a more intuitive idea of the type of variation you're looking at. In this case, for the PC1 case, now what we observe is that, first of all, generally see this kind of a up and down shift, right? It has this type of variation. And second of all, the sort of this up and down, it's not exactly like a constant shift, right? You see the variation at the beginning between the three curves are a little bit smaller, but then they gradually increase. Maybe somewhere around here, you see the largest variations, right? And then from here onward, the variation becomes smaller again, right? So you see, so overall you would probably see this is like more like up and down shift, but then the variation among actually first increase and then decrease, right? So this is like a little bit more intuitive to help us understand what the type of variation we are talking about. Similarly, we can look at the second principal components, the third and the fourth. Yeah. Yeah, so I think that's all for a principal component analysis. So I think if you the takeaway message is really, I would say, is like I would really view this as like a feature extraction tool. It helps us understand what the type of variations are important in those trajectories. It also acts as a dimension reduction or feature extraction tool. So we are able to reduce a lot of data points for each individual trajectory into a few summary score. But the good thing about this is like we also know that this summary score, we are able to control how much information we keep, how much information we remove, right? So if you choose a threshold, let's see, 90%, you know that even though you only use a few summary scores, you still capture the majority of the information. So I think that's sort of the main benefits of this PCA analysis. So I think maybe I'll pause briefly here and see if there are any questions. I don't see any questions in the chat. So Okay, so if there are no questions, then we'll keep going to the next part. The next is the final part, which is like, okay, so what type of analysis we can do with this type of data? So generally speaking, I would say consider, we can, of course, we can wanted to explore patterns of the functional data, or variations among trajectories, and we might want to do some regression analysis. This kind of trajectories may serve as an outcome, right? You might want to see, let's see how different subpopulations, how their patterns differ among different subpopulations. You might also be interested in using these patterns to predict, as a predictors to predict outcomes. Like the question would be, among individuals with certain trajectories, how do they predict certain outcomes, right? So I'll just maybe outline 3 different approaches, and again, to the focus is more like on the concept and the idea, not necessarily the detailed, technical details or implementation. So the first approach is what I call through pre-specified scientific features. What I, generally all those approaches, they have generally 2 steps. One step is feature extraction. What type of feature do we want to extract? And the second is like, how do we use those features in the regression analysis? So this first approach is from the so-called pre-specified scientific features. Typically, what this means is that, maybe you have like a scientific knowledge or scientific hypothesis. You kind of know what features are scientifically relevant, and then you can sort of construct those features by your knowledge. Now, just to give some examples, you could think of like, let's see, if you're looking at the growth curve, right? You can think of, let's see, the average values, the mean, which could be one important feature. You could think of like the average slope, even though I guess it's not necessarily linear. You can still use the average slope, let's see, as another feature, right? You could, if you know that, for example, there are different stages of growth, you can probably divide the time interval into a few parts, maybe like the earlier, early part or the later part, right? In each part, you can calculate, let's see, a mean or average or slope, right? So you can construct a few different summary metrics or features depending using your scientific knowledge or hypothesis. As a so I'll in my notation I would say start from this xi of t, which is your trajectory, you convert them into features like ci1 up to cik. They are key features you decide to use, and then this because they are pre-specified or predetermined, so you have like your own formula in terms of how to extract those features, right? So you don't have to estimate those from the data. After you get the features, you can put those features in the regression model. Maybe you can also control for some additional covariates ZI and fit depending on what outcomes you have. If you have a continuous outcome, you can fit a linear model. If you have like a discrete outcome, you may fit logistic regression or Poisson regression. Or if you have time to event outcome, you can fit a Cox regression models, right? So then you can get coefficients for each of the features. So this is one approach that one can take. But of course, it has pros and cons. The pros is like because since you know what each feature really means scientifically, right? So this model typically is very interpretable. But on the other hand, the cons of this approach is that so you kind of have to know what features you want to use and how many features to use, right? Because if you use too few of them, like let's say if you only use a mean or the mean plus slope, for example, you know that you're only capturing like linear trend in the data, right? You're going to probably miss some important information in the data. But if you decide to use too many of those features, that you may also run into other problems like multiplicity. You know, if you want to test significance for them, you have multiple testing problem. Potentially, some of them might be correlated with each other. You have collinearity issues, right? So, so generally, and also like for the selected feature set you have, you don't really have a good control of how much information did you keep, how much information did you miss, right? So I think that uncertainty is also something you want to keep in mind. So it's if you are lucky, maybe the features you have, like you capture most of the important ones. But if you are unlucky, maybe most important you actually missed the most important ones, right? The second approach, I would call it like adaptive features, or using something like the principal component analysis. So for the feature extraction step, we're going to adopt the principal component analysis. So from our original trajectories, we get a set of like summary scores, the PC scores like DI1 up to DIJ, and we choose a J number J so that let's say we explain 90% of the variation, right? And then in the second step, you can put this regression scores in you can put these PC scores as predictors in your regression models and fit your typical regression model. Now again, this approach has its pros and cons. The pros is as we explained earlier, you know, the PCA by design, it's a very nice dimension reduction tool. So meaning typically you only need a small set, typically only a small set of scores to explain most of the variation. And also more importantly, you have a control of how much information you keep, right? If you use a threshold of 90%, you really feel comfortable knowing that the most important features is already there. So you don't have to worry about missing those. As in the other benefit is that the PC score by design, they are uncorrelated with each other. So you avoid potentially collinearity issues. But on the other hand, the limitations of this approach, I would say, is generally lack of interpretability. So like you know, those features, you know, as we mentioned earlier, we try to explain what these principal components are, but sometimes they are still not very easy to interpret, right? So yeah, and also since the features are data adaptive, they are also like population dependent in the sense that you know, if you do a PCA on one population, one particular data set, you extract, you know, a few features, right? Principal components. But then if you wanted to apply the similar method to different populations, as you might extract a different set of features, right? So those they probably would not extend easily across populations. Okay, so I've just I will expand a little bit on this approach and also illustrating that this is kind of how it works, but you can also get another quantity as your output, which is potentially useful in many scientific contexts. So what I wanted to go through is that, you know, we can think of in this case, let's say you have a scalar outcome, you have this functional data or intensive longitudinal data as your covariate. So we can think of like a regression function conceptually, more like, you know, let's put the whole trajectory into the model. As an xi evaluate time tj, right? Let's have a coefficient beta j at each time point. Okay, so generally speaking, if you just fit this model, let's see, using least squares, it's not a good idea because you have too many covariates, right? The number of covariates probably sometimes even larger than the sample size, then you really run into problems, right? So if you directly run this, is not a good idea. But there are techniques where you can add some sort of regularization to still estimate those coefficients. As in, if we have really a large number of time points, you can think of the summation become an integration, integrating over the whole trajectory, and your coefficients become a coefficient function itself. It become a trajectory, right? Beta t really shows your covariate, your trajectory at time point t has an effect, which is beta t, right? We do allow that effect to change over time. So this is what this model means. And in terms of how do we fit this model, we can still do the principal PCA, but the benefit is that once you fit the model, you get all the coefficients. You can go back and estimate this coefficient function called beta t. So I wouldn't go to the technical details, but just wanted to mention that this is something we can estimate. And this is an example showing you why this might be useful. This is like a functional regression, like again the scalar function regression with this MATLAB data. So the covariate functional covariate is really the growth curve, the ad count trajectories over time, right? Over 25 days, basically. And I think I think I forgot what the outcome is, but there must be like some one scalar outcome. So if you run like a functional regression like this, so you can again you think of really throw the whole trajectory into the model and try to estimate all the coefficients in a smart way so that you can fit the data fine. So you're going to get a beta coefficient, a beta t, something like this. The curve in the middle is our estimates, and then this band here give us about 95% confidence band. So this is interesting because what does this curve beta t mean? It really tells us the effect of this trajectory at any time point, right? It will show that, let's see, 1 unit increase in this egg counts at time 0 has the effect about close to, let's say, close to 1.4 or 1.5, right, at the beginning. But then the effect gradually declines. And once you get to somewhere around 15 days, the effect become almost zero, and it's not statistically significant. And then effect become negative between 15 to 20 days, and its increase at the end goes up a little bit again. But here the confidence band covers zero. It's not really significant, right? But I think the nice thing about this type of model is it gives you this more like time varying effects of the trajectory, right? You are able to tell your trajectory at different time points could potentially have a different effects on the certain outcomes. Yeah, so I think this is like one of the benefits with this this second approach. Basically, I would call it like a functional approach through PCA. The third approach is from still use data adaptive features, but more like using clustering methods. Clustering, I think, is the way this works is you have again the original trajectories, right? You have maybe up, let's say, 100 observations per subject, but you want to group them into a few different types, right? MI, let's if you assume there are big M different types of trajectories, and each individual belong to one of those groups or clusters, right? So you would the first step of the feature extraction is we run a clustering algorithm. From the trajectory you get to a cluster membership, so everybody belong to one of these clusters. And then the next step, you use these clusters maybe in the regression model. You can use them as an outcome or as a predictor and run further regression analysis. And I do want to say that there are different types of clustering algorithms that has been developed. So one approach, you could use PCA first. You could use trajectories, do a PCA, and generate your PC scores, and you run a clustering algorithm on the PC scores, and then you get your clustering. And there are also other methods where you don't have to do PCA as an intermediate step. You can just, using like something like mixture models directly to get clustering. But regardless of which method you are using, I think the general principle is that try to group the trajectory into a few different types, and then using them in further analysis. I'll just maybe I think next I'll illustrate an example from one of our recent projects to see how this approach works in practice. So this example is it's in collaboration with Dr. Jonathan Baker. He's a faculty member at Fred Hutch and UW as well. His group has been using smartphone apps or to help people quit smoking. So he ran a few randomized trials to test the efficacy of different smartphone apps. This is one of them where we wanted to look at the app usage trajectory, app usage trajectories. So this figure shows you like more like the raw data. So like this is in daily level, I believe. So there are each row here. We typically call this lasagna plots. So each row here is one individual. So there are about 218 days for each individual. And then for each individual in each day, we have like a binary outcome. We know if they used the app or they didn't use the app. If they use the app, it's coded as 1. If not, it's coded as 0. So if you look at this line, so this person probably didn't use the app maybe until around here. And then they stop using it again. He or she only probably use it like a few days in the middle. And whereas this individual, and then also like the darker color here means usage, light color means no usage. So the last person is like more consistent user, right? This person probably actually used the app pretty much from the beginning, in most of the days until almost here. There were like a few days in the middle where I didn't use it, but for the most part, I use it very consistently, and then dropped out at this point, right? And then you can see many other patterns within in the middle as well. So this kind of the type of data we got. So what we did is actually we first because the data originally is like a binary data, right? So we actually first do a little bit of pre-smoothing, like we group them into for every week. So like so we can calculate the percentage of days using the app within each week, right? So that percentage will become more like a continuous variable, and then we are able to sort of fit functional clustering algorithms. So from the clustering, we identified 3 types of clusters. So this one on the top, this shows like the average days logged in per week. So yeah, so this group, start with somewhere around between 5 and 6 average, 5 to 6 days of usage per week, and gradually decline. Maybe at around week 10, it's dropped to about 3 times per week. But then it still keeps using the app, right? Even towards the end, it still kind of have a frequency of closer to 2 times per week. So they are sort of like more consistent users throughout the study period. And then there is this group, they actually started with decent usage, like on average, maybe close to around 4.5 days per week. But they drop more quickly, after about 4 weeks, it's kind of a drop to below one day per week, right? And then somewhere around here, it's almost like they're not using it anymore. And then the last group, we call them like more like 1 week users. So even at the beginning, they really only use the app for about 2 times per week. And then in the second week, it's already dropping to very low levels, like less than maybe like 0.3 or something, 0.3, 0.4. Yeah. And then in the third, then it gradually dropped to no usage very quickly. Yeah. So yeah, so this is what we are able to get the 3 types of trajectories. And then the bars you see here, I think shows the variations, like about the 90% coverage, the type of trajectories. So that means for the people in the first group, the average trajectory is like this, but an individual could have something like here or maybe from here. But generally speaking, they still have like relatively high usage across all times. Yeah. Um, and then, so after we obtain these different patterns or clusters or trajectories, how do we use them in further analysis? So this result is in this is a randomized trial. So the endpoint is I think 12 months smoking cessation outcomes. So that's like so the quit smoking after 12 months. That's the outcome. It's a binary outcome. So we run logistic regression of this outcome versus the clusters of the smartphone usage patterns. So the reference group was like, remember we have this 1 week users, 4 week users, and 26-week users, the 3 group labels. So we use the 1 week users as a reference. And with this table shows you the estimated odds ratio and p-value for the other 2 groups, 4 week users and 26-week users. So you can see for 4 week users compared to 1 week users, their odds of quit smoking is 1.5 times higher than the 1 week, right? So it means like so people actually use 4 week users actually have a higher chance of quit smoking, and this is statistically significant. And the 26-week users, they are like really more consistent users of the app. They have even much higher chance of quitting smoking. The odds ratio is very high, almost 5, and it's highly statistically significant. Even the confidence bands is, the lower bound is 3.3, the upper bound is 7.5. So I think this really shows us that, I think we all know this, right? Like, of course, if the app is well designed, if you use it more often, you have more chance of being successful, right? But I think it's still good to sort of visualize those patterns and quantify their effects. The next issues we use the smartphone usage trajectory as the outcome and try to predict app usage trajectory patterns based on some baseline covariates. So in this case, we are running because there are 3 groups, right? 1 week users, 4 week users, 26-week users. So we run multinomial logistic regression models using 1 week user as a reference, and then see how different covariates, baseline covariates, predict people's tendency of being having different usage pattern, right? So if we focus, let's see the number here. The covariate is smokes less than 10 cigarettes per day. So we see an odds ratio of 1.25, even though it's not statistically significant. But what this odds ratio means is like compared to 1 week users, it means like people who smoke less than 10 cigarettes per day have a higher chance, like maybe 25% higher chance of being in a 4 week user compared to a 1 week user. So I mean, like people smoke a little bit less, they have, a higher tendency to use the app more often, basically, right? So compare 4 weeks versus 1 week is not significant. But if we compare 26-week users versus 1 week users, the same variable, the odds ratio is now 1.9. It's much higher, and it's statistically significant. So again, I mean, the conclusion is that, participants who smoke less than 10 cigarettes per day, they have a higher tendency to be like more consistent users of the web of the smartphone app. Yeah, I think that's just showing you example of how in this kind of real smartphone based smoking cessation trial, how do we actually use this type of data to answer scientific questions. The next one is actually somewhat similar to this, but I think since we have time, I probably would go through that quickly too. There's some lot of similarity with smartphone app, but has also a little bit of unique features as well. This example is we wanted to understand adherence patterns from widespread devices. So the context is like this is in collaboration with my collaborators, Dr. Yinjin Chen and my former staff scientist, Yifan Zhu. So like the context is like it's a HIV prevention trial. We use the so-called white pill device. So like every participant, they are asked to take 2 pills per day for HIV prevention. And then they are supposed to take 1 pill in the morning, 1 pill in the evening. And then since we all know that, adherence is an issue, especially in prevention trial, right? If you are not sick, then you might not be willing to take, those medications, right? So adherence, we all know is kind of a big issue. So this trial used a wise pill device in an attempt to better quantify adherence. So basically you have like a pill dispenser and they have a cell phone chip. It sends signals. So every day, every time they open a bottle, the coordinate center will receive a signal. So we actually know for each person. So the trial run about for 1 year. So we're showing you like a few different individuals. The raw data is over here. So like for each day, you have like a value of 0, 1, or 2. 0 means not opening the bottle at all. 1 means open it 1 time. 2 means open it both times in the morning and in the evening. So ideally, we want them to open 2 times, right? But in practice, of course, you see all types of the patterns. So in this figure, the white background meaning 0, no opening. The light shades meaning they open it 1 time. The darker shade meaning 2 times. So we can see the first individual. This person actually takes a pill like for most of the days, but they often do it like for 1 time instead of the 2 times, right? But they also sometimes they sort of didn't open the bottle at all. And this person is probably like highly adherent, right? This person generally take 2 pills for most of the days, even though there are some days intermittently maybe they forgot to take it. And this person is like, the adherence level is relatively low, right? So they probably only takes pill up to about 70 days of the trial, first 70 days of the trial. Even among these days, there are many days with no pills taking or only one pills. And after about 70 days, it's kind of completely, forgot to take to open the bottle. Yeah, so this is kind of show you the type of raw data we have. So again, very intensive longitudinal data or functional data, but also it has another distinctive feature. Is like the data is discrete, right? So it's like 0, 1, 2. It's not really continuous. So I didn't even mention in the talk because the discrete functional data is even more challenging. It's actually still an active research question for statisticians. So what we try to do is we try to pre-smooth the data, transform them into like continuous data, and using sort of more existing methods. So the right-hand side shows the type of smoothing we do with, we actually choose like 7 day as a window, right? You choose for the 7-day window. They are out of like 14 different times to for pill opening, the bottle opening, we can count how many percentage of that did they actually open the bottle, right? So you would have a percentage at each time point. So we choose 7-day like moving windows. So the each of the time, you can see they probably start at day 7, I think. Day 7, that would give you the percentage of the first 7 days, and then it's throughout the whole year. So this it kind of gave us an idea of how their adherence percentage change over time, right? It's probably a little bit more intuitive than the left-hand side. So in this case, you can see this individual number 6, we kind of already know it's a highly adherent individual. Like, the percentage really stay really high, most of the time above, sometime between 90% and 100%, pretty much throughout the whole study period, right? So, very good example. On the other hand, there are, let's see, the individual, um, I think probably the figure, there's a little issues here. Like the individual 12, it starts with maybe somewhere around 60% adherence, but it's dropped to 0. I think it's probably not showing here. And then there are 11, yes, 11, yeah. So and the 18 is more like intermediate. So adherence patterns. And similarly, we run a clustering algorithm on all those adherence patterns. So we generally obtain 3 different clusters. So the cluster number 1 is individuals generally have a higher adherence, generally speaking. And so their average adherence percentage is about it starts maybe somewhere around 80 to 90%. At the end, it's probably dropped to somewhere between 70 to 80%, but still relatively high throughout the whole study period. The cluster number 2 is, it starts a little bit lower, but then they drop more rapidly, right? Towards the end, the average adherence drop to somewhere around maybe 40% or so. Cluster number 3 is the lowest one. So the average starting point is around 60 to 70%, but you see a lot of variation. Some of them, like at the beginning, only have about maybe 30 to 40% adherence, even at the beginning. And then they also drop more rapidly, and maybe after about 5 months, they kind of generally drop to very low levels. Yeah. So these are like the 3 clusters we identified from the functional clustering algorithm. And I think we did some additional regression analysis as well using this cluster membership either as an outcome or as a predictor. But I think this will be very similar to the smartphone example, so I didn't show the details here. Okay, so yeah, so to summarize, so the intensive longitudinal data and functional data, so they require special statistical methods because because of the correlations, but also more importantly because of the intensive data. So the type of trajectories are just much more complicated, and then the covariance structure is also more complicated than our standard longitudinal data. So so we generally wanted the model to be more flexible and making less assumptions. As in we talked about curve nonlinear curve fitting methods using penalized splines, and I think the part I didn't get to again, that's probably too technical. So like it's an advantage of the penalized splines is there's some way to implement the splines using random effects or mixed model framework. So that's too technical, and you guys probably don't even need to know that. You can just use existing packages. But because it's framed with in the mixed model framework, you can combine that with in longitudinal design, hierarchical design, a lot of these things, and the nonlinear effect. You can combine all the components together very nicely using the same mixed model framework. So that's actually have a lot of advantages in the actually implementing the methods. And then I talked about exploratory analysis of those type of data. In particular, I highlighted the principal component analysis because I think, as we mentioned, it's even difficult to understand the variations in the data without methods like PCA. So it's really important, and it can help us identify the most important directions of variations. And then finally, also briefly touched base on the functional regression and the clustering, as especially using example to show how to do this analysis in actual projects with wearable and mobile devices. So yeah, so these collaborators I mentioned, they are in some of those projects like Yifan Zhu, Yin Chen, and Jonathan Breaker. And then there are also on the technology grants, the BIRCH grant, also my own grants, which is devoted to develop methods generally along this direction, with the functional data analysis and wearable mobile devices. I think that's all I have. I'll stop here.